The double and half angle formulas. We have a total of 6 that we could be looking at. Okay, so we have the double and we have the half, but we also have each of those for the sine, the cosine, and the tangent. Okay, what I'm going to be doing in the video is deriving the double angle formulas for the sine and cosine. The double angle formulas are really just a special case for the alpha plus beta. Okay, so if we had the sine of alpha plus beta, or the cosine of alpha plus beta, or even the tangent of alpha plus beta. But in this special case, the alpha is going to be equal to the beta. The angle measurements are actually just the same size. So if we use the fact that we know these, what we can actually do is just substitute in either alpha or beta so that we have the same angle measurement, and treat this as maybe alpha plus alpha, which alpha plus alpha would just be 2 alpha, right? These are like terms, so we get 2 alpha. Hence, we can call this the double angle formula. All right, for the sine of 2 alpha, what we can do is backtrack to a formula that we know. The sine of alpha plus beta is equal to the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta. But we don't really have an alpha and a beta. Alpha is equal to beta, and that's how we get alpha plus alpha. So what we can do here is substitute an alpha in for the beta. And if we do that, we're going to get the sine of alpha times the cosine of alpha plus the cosine of alpha times the sine of alpha. All right, so let's take a look at these. We got sine alpha times cosine alpha. We also have cosine alpha times sine alpha. These are actually the same thing. This is that. We just have them flip-flopped, but by commutative property, they actually are the same thing. And if you're adding two things that are the same, you can actually combine like terms. We can write this as 2 sine alpha cosine alpha. All right, so the sine of 2 alpha is equal to 2 times the sine of alpha times the cosine of alpha. Let's see what cosine of 2 alpha would look like. Okay, so we'll backtrack here. 2 alpha would just be alpha plus alpha. We'll continue to backtrack all the way to what we know. The cosine of alpha plus beta is equal to this. It's equal to that. Now, if we're going to substitute an alpha in for the beta so that we can get 2 alpha, we're just going to change each of the betas to alpha. That will give us cosine alpha minus sine alpha sine alpha. All right, so these are not going to be like terms, not like what we saw above, but these two are identical to each other, which means you could just write that as cosine squared alpha. And these are also identical to each other, which means that we can write them as sine squared alpha. So the cosine of 2 alpha would be equal to cosine squared alpha minus sine squared alpha. A neat thing about cosine 2 alpha, when you see it structured here, you might recognize a little bit of that as coming from the Pythagorean identity, the first Pythagorean identity that we have, right? You've got the cosine squared alpha, the sine squared alpha here. Of course, these are not being added together, so that doesn't mean you can take all of this and then just call it 1. It's not going to be that convenient. However, you can solve this Pythagorean identity for either one of these two, right? Suppose that we were to solve for the sine squared alpha. Suppose we solve for that. Sine squared alpha would then be equal to 1 minus cosine squared alpha, right? We just move that over to the side. And if we do that, we can actually take this expression and substitute it in here. You could substitute it into that spot. All right, so if you were to substitute that into this equation, you would get cosine squared alpha minus, and I got to use parentheses here because all this is going to get subtracted. You're going to minus 1 minus cosine squared alpha. Okay, so you're going to have that negative distribute in, which will give you a negative 1. It will also distribute here, giving you a positive cosine squared alpha, which will then group with the other one and give you 2 cosine squared alpha minus 1, which you're going to notice here. Okay, so using the Pythagorean identity and solving for either the sine squared alpha or cosine squared alpha, we can substitute into this and create new formulas. All right, the other one, that would be created by solving for cosine squared alpha. If we solve for that and had 1 minus sine squared alpha, you could substitute that in here, and then you'll see that it simplifies down to that. Okay, so we actually have 3 formulas for cosine 2 alpha. We have this one that uses cosine and sine, but then we have the others which will either just use sine or just use cosine, which is what gives some benefit to these. Example 1, if the sine of alpha is equal to 4/5 and alpha is located between 0 and pi over 2, that means that it would be in the first quadrant. If we have that, then let's go ahead and find the sine of 2 alpha and the cosine of 2 alpha. All right, so since the way that this is being described at the beginning, what I'm going to do is go back to making that circle and just sort of getting everything organized. All right, so alpha is going to be a first quadrant angle. And by definition, the sine is the y value divided by the radius. Okay, I think it's actually going to be tilted just a little bit more vertical than right down that diagonal. All right, so I'm going to build the right triangle. The 5 is going to be the radius, and then the 4 is going to be the vertical, the y value. So that means that our x, our horizontal here, would be a 3. Okay, that would be a 3. Let's write that a little bit better. And I drew this a little bit small here, but look, I'll just mark it there. That's alpha. So alpha is a measurement that goes from the positive x-axis up to that location. And what we're going to be figuring out is how we would evaluate the sine if we double that angle. Okay, for a bit of perspective, let's do something here real quick. Let me take the arc sine. Let me take the arc sine of 4/5. So we can see this in degrees. Okay, so this is actually going to be a 53-degree angle, which means that it is a little bit beyond the halfway point here. It's past 45 degrees. And if we double that, we get 106. We get 106 degrees. So we are actually going to be evaluating these by using 106 degrees, which means that you are going to be in quadrant 2. And I want you to remember that because in quadrant 2, the sine will be positive, but the cosine will be negative. And I want to see that happen at the end of our calculations here. All right, so the sine of 2 alpha. The sine of 2 alpha is equal to 2 times the sine of alpha times the cosine of alpha. Okay, well, the sine of alpha is 4/5. Cosine alpha, we've got our picture, so that will be 3/5. So all we need to do here is multiply these and see what we get. The bottom is going to give you a 25. The top is going to give you 24. That'll give you 24, and that's the answer to it. That's what we get. All right, let's check out the cosine of 2 alpha. Cosine of 2 alpha. For this, you have different choices in what you can do. The original formula that we come up with uses both of those, and I'll probably just go with that one. The other ones either use sine or cosine, so you can just sort of choose what you want to do with it. What I'll do is, I guess, just use that one. It doesn't really matter because you do have the cosine and the sine for this situation. Okay, so I'm going to take the cosine squared alpha, and subtract sine squared alpha. All right, so cosine squared is, cosine is 3/5, so that'll get squared, and then we're going to subtract 4/5 squared. All right, so when they square, you're going to get denominators of 25 here and there. Okay, so that's kind of convenient because it matches up to what we've got happening there. So it is going to be 25. The tops, you're going to end up with 9 minus 16. Okay, 9 minus 16, which is going to give you -7. You're going to get -7. All right, so thinking about where that angle ends up, that it ends up in quadrant 2, that does match up because quadrant 2 is positive for sine, but it's going to be negative for cosine. Matches the values that we have. All right, let me go ahead and do one more thing here, which is just verifying the calculator that this does work out. Previously, I had taken the arc sine of 4/5, and I got that number 53. And then if I doubled it, I got that value 106. All right, what I'm going to do in my calculator is I'm going to save that number. I'm going to store it. So if you have a calculator like this one, there's a button STO. I can store that number under any letter. So I'm going to save it as letter A. Save this. That's my double angle. Remember, that's the double angle. All right, so now my claim here is that if I took the sine of that angle, the doubled up angle, if I take the sine of that angle, so I'll just type in A, I get that value. And I believe that that's the same thing as 24 divided by 25. And it is. All right, I'll do the same thing for cosine. The cosine, and I'll plug in that value. By the way, I stored that value. That way it would have all the decimals that went with it, and I could see exact comparisons to these. All right, so the cosine of the 106 gives us that. Notice the negative. And -7 divided by 25 is exactly the same thing. In example 2, we are asked to show that the sine of 4x is equivalent to all of this stuff here. We got to show that the sine of 4x is equal to all of that stuff that we have there. All right, so let's take a look at sine 4x. We've been talking about sine 2x. We've been talking about that one. Well, sine 4x is actually just 2 times 2x. We can think of it that way. So we start to draw a connection between this and what we've been looking at with the double angles. It's just a double of the 2x. Okay, so I got double 2x. Now, if I refer to the formula that we've got for the sine of 2 alpha, refer to that one, it would be equal to 2 sine alpha. In this case, our alpha is the 2x, so 2 sine x times cosine 2x. All right, that looks pretty good. Actually, it looks nice, but it does not go as far as what this wants us to do here. Okay, so what else do we got? Well, within each of these, you actually have your own double angles, right? You got 2 times x. You got 2 times some other value that's in there. So we should be able to expand out each of these. Okay, so we're gonna have that too, and I'm gonna go ahead and put some brackets in here because I think the expansion of this is gonna end up, well, I know it's gonna end up creating some sort of a subtraction. Okay, so I'm gonna keep that just outside of everything for the time being. Sine 2x, that will be 2 sine x, cosine x. So I'm pretty much doing the same thing I did from here to there, except I just have regular x's. All right, and then for cosine 2x, that is gonna break into cosine squared x minus sine squared x. All right, and now since that one created some subtraction in there, and we had multiplication happening earlier, we are gonna need some parentheses here just to keep all that contained together. And that should be all of it, and now it's just a matter of maybe moving some things around to get to that point. Okay, so we can go ahead and distribute that 2 into this stuff, and when it does that, it really only needs to go to the front part. That will give you 4 sine x cosine x. Okay, and then we've got this difference over here. All right, we're able to drop the brackets now. And we'll go ahead and distribute that in to both of those terms. So you can have a 4. Let's see what happens with all of this. You've got a sine x. The cosine x can actually, in a way, group with these. That would give you cosine cubed x. All right, then we got our subtraction. The 4 is going to distribute in as well. The sine is now going to multiply with these signs and give you sine cubed x. And we've got a cosine x that also has to go over here. Doesn't match with anything, but it's just gonna hang out there at the end. And let's see if we've got it. 4 sine x cosine cubed x, 4 sine x cosine cubed x, minus 4 sine cubed x cosine x, minus 4 sine cubed x cosine x. All right, there we go. As mentioned at the beginning, I was only going to derive the double formulas for the sine and cosine. The rest of these are the remaining formulas. The top 2, these are going to be the half angle formulas for the sine and cosine. The bottom 2, this is the double angle formula for tangent. Over here, we have the half angle formula for tangent, except that you actually have 3 different options in how you want to set those up.
Later, blah.